Hey Arno, glad to have your question. I thought I'd just do a little video to show you what the answer really using TechnicVR from Shaderware. So basically we are all taught about these X-ray spectrum spikes, as you asked in the question, these characteristics. So these are K-shell electron, tungsten K-shell electron characteristic energies, but a tungsten atom doesn't just have electrons in the K-shell, it also has electrons in the L shell, the M shell, etc. So K are the ones which have got the most energy, and so they're the highest energy spikes. And adding filtration is not really going to alter those specifically or remove them. We can add some extra filtration here. I'll show you. If we add some copper filtration, for example, let me just expose this so that we've got it fixed. So just to orientate people, along the bottom of this graph here we've got photon energy, and along the y-axis we've got the amount of energy, or the amount of photons of each energy bin. So you can see that we've got very few low energy photons, below 20, and that's because this X-ray tube has 3.2 millimeters of aluminium filtration. It's also got the glass of the tube window. Even though it's made of beryllium, it still filters some. And then of course there's the tungsten. A lot of the X-ray photons are actually generated within the tungsten of the anode, and so they have filtration as they're coming out of the tungsten filters them. So for all those reasons, inherent filtration exists. So we lose a lot of energy here, and then we're starting to get the energy as a peak. So we get the mode, if you like, the most common photon energy, if we ignore the characteristics, is going to be around the 40. I think we're setting, this is a 90 kVp beam, 5 ms. So the most photons from the bremsstrahlung, which is the smooth curve, will occur at about 35 in this beam. Then we have the characteristics, and of course, so the real mode is this one here. So there's if you say which is the most common photon energy, it is the most photons with the most is going to be around 50 something, which is the characteristic, one of the characteristic energies of the K-shell electrons. Okay, so that's what these are. And if we add copper filters, as you said, what will happen if we add copper filters? Do they remove the spikes? I did expose that, didn't I? So why isn't there a beam? Oh, I have to choose it as the default one. Yeah, okay, so now if I add the copper, you can see what's happening. By adding copper filtration, then we are dampening down the spikes, but we're actually having more of an effect on the bremsstrahlung than we are on the characteristic. Yeah, so adding the copper, I mean, you would never have, is dramatically reducing the amount of bremsstrahlung in the low energies. And now our median energy, if you like, going from somewhere around 35 is now the median energy is somewhere around 65. So we've massively increased the one measure of the average energy of the beam. So this beam is going to be much more penetrating than this beam. Having said that, there's a lot less photons in this beam because a lot of them have been attenuated, so you'd have to increase your MAS to get the more penetrating beam than this beam. So anyway, now then, in answer to your question though, do we remove the spikes, characteristic spikes? The answer is yes, because what we're not seeing here, because of the inherent filtration, is the L shell spikes of tungsten. So if I remove the inherent filtration, if I was to take the aluminium filter right out, in fact if I turn that to 0, So now I've taken the aluminium filter completely out, which is something that you would never do, and legally I think all X-ray tubes must be filtered, at least if they're capable of 70 kV, then they must be filtered. I think it's 1.5 millimeters of aluminium must be added, and the reason for that is because of these extreme peaks, characteristics that I think these are the L shell characteristics, which occur around 10 to 15 kV, and they're useless to the diagnostic range. They'll just be absorbed by the first couple of millimeters of the patient's skin, maybe a little bit deeper than that, but only by the skin. And so these are radiation, potential harmful this is potentially harmful radiation, which shouldn't be anywhere near a patient. And so we put filtration in to remove these characteristics, and as we add the aluminium filtration, you can see a very small amount of aluminium filtration will take these spikes out completely. Yeah, so 0.8 of a mil. 1 mil of aluminium filtration will remove those L-shaped spikes, not shaped, but those L energy level electron spikes, leaving the K shell electron energy spikes in place. And as I say, the legal requirement, I believe, is 1.5 mil of aluminium, and most X-ray tubes will have nearer, in the modern era, most X-ray tubes have nearer 3 mil of aluminium. We model a tube, our basic tube that we model is 3.2 mil of added aluminium filtration, and then you add copper, and we've already seen how that works. So that's the answer to your question. Thanks for asking it.